Hello everyone. So this class we're going to do a quick review session of our contents that we have learned since our first exam. So as you can see, after the first exam, we mainly covered the water quality and water treatment. And specifically, this part of water treatment is for drinking water treatment, right? So after the second exam, we're going to cover the wastewater treatment. But here, let's just focus on these two parts of the contents. So first, regarding the water quality, we use the first class to talk about the sources and different types of the water systems. So as you can see, there are many types of different water pollutants, and also different types of the water systems. And specifically, we're quite interested in river water because a lot of the drinking water is coming from the river water. And in terms of the river water, people are very interested in the oxygen demanding materials. So basically, these are the organics or contents that will require oxygen to get them oxidized, right? So let's say if we have a river and then basically those organics that's dumped in the river or those pollutants that's dumped in the river, they will need oxygen or they will need some bacteria to get these organic species to fully get oxidized, and then we can basically purify the water. Okay, so this involves the definition of the oxygen demand. Okay, so this is the amount of oxygen that's required for us to fully oxidize these chemicals. And in terms of the oxygen demand, we introduced that there are three different types of the oxygen demand. So one is called the theoretical oxygen demand. For example, so basically this theoretical oxygen demand is just purely based on the stoichiometry, right? So if we talk about the carbon as an oxygen demanding material, then you can see that it's going to form carbon dioxide. So what that means is that 12 grams of the carbon is going to require 32 grams of the oxygen. And so therefore, the theoretical oxygen demand for 1 mole of the carbon is going to be 32 grams of oxygen, right? And in terms of the chemical oxygen demand, this involves the chemical reactions. So basically, instead of calculating based on the stoichiometry, we can use some strong oxidizing chemicals to oxidize the organics in the water, right? So in this case, the oxygen demand or the chemical oxygen demand might be different from the theoretical oxygen demand. And the most important parameter that we learned through is about the biological or biochemical oxygen demand, okay? That is the BOD. So what happens is that, let's say, inside this bottle is the river water that we sampled. In the river water, there are, of course, pollutants or organics in the water, but at the same time, there are some microorganisms. And these microorganisms are going to utilize the remaining oxygen that's in the water and then to oxidize these chemicals in the water. Okay? So the amount of oxygen that's required during this process is called the biological or biochemical oxygen demand. Okay, so if we talk about the BOD, we have to go through this curve here. So what this curve represents is this concentration of the organics that's in the water as a function of time, and also the BOD as a function of time. Okay, so if we think about that bottle that we showed on the last slide, if we want to measure the concentration of the organics in the water, we know that because of those microorganisms, these chemicals or these organics are going to get oxidized. And this is going to reduce the concentration of these chemicals, right? And we know that this is a first order reaction in terms of the decomposition or the oxidation. So that's why the concentration of the organics are going to follow this curve here. And this is an exponential decreasing curve. So basically, what this represents is the remaining organics in the water. Okay, so L is the remaining organics. And we know that the L follows the exponential decrease, which is L0 multiplied by exponential minus KT. Okay, so as time goes to infinity, the remaining organics concentration are going to go to 0, okay? But we should also pay attention that the L is not equal to BOD. So L is the remaining organics in the water, or the remaining chemicals in the water. But if we talk about the BOD, which is about chemical oxygen demand, so the demand of oxygen as a function of time is always increasing, right? So at the beginning, the oxygen demand is 0 because it didn't consume any oxygen in the beginning. Well, at the end, the BOD is the highest because it almost consumed all of the oxygen in the water. So the BOD is going to follow a curve that's reciprocal compared to the remaining organics, right? So there's a clear difference between the remaining organics and the BOD. So the BOD, therefore, is just calculated by L0 minus L0 exponential minus KT, okay? So the L is the remaining organics, right? While the BOD is basically the reacted organics in the water, okay? So we can further calculate that by L0, 1 minus exponential minus KT. Okay, so we need to pay attention that the BOD is always increasing, while the remaining organics is always decreasing. And therefore, we introduced the concept that there is an ultimate BOD, which is the highest or the largest BOD a water can have. Okay, so that's going to have this value here. And as you can see, when time goes to infinity, then BOD, ultimate BOD, is going to be equal to ultimate BOD is going to be equal to L0. Okay? So again, the BOD is always increasing as a function of time, while the remaining organics are decreasing as a function of time. Okay? So here is an example that we went through during our class. So basically with this concept, let's say that if the 3D BOD have a 3D BOD have a value of 35 milligram per liter, and that we know the BOD decay constant, right? What is the ultimate BOD? So we can use the equation that BOD3 is equal to L0, 1 minus exponential minus KT. All right? So that's going to have L0, 1 minus exponential minus 0.345 multiplied by 3, right? And the 3-day BOD is equal to 75 milligram per liter. Okay, so based on this relationship, we can calculate what is the ultimate BOD, which is 75 divided by 1 minus exponential minus 0.345 multiplied by 3. And the final value is actually 75 divided by 0.645, which is 116 milligram per liter. Okay, so this is a concept of basically calculating at any time, right? And as you can see in your homework, we did quite a lot of practice calculating the BOD with different values. So basically, if we know the BOD at a certain day, let's say BOD 5, BOD 3, we can calculate what is the ultimate BOD. And also, if we know the ultimate BOD, how can we calculate the BOD 3 or BOD 5? We can just directly use this equation here, right? So one thing we need to pay attention is also this reaction rate here. So the reaction rate is typically assumed that it has a value under 20 Celsius. But as we have introduced before, the higher the temperature, right? The higher the temperature, the higher the reaction rate. And because of that, the reaction rate can be calculated based on the relationship shown here. Okay, so if we have a higher temperature, basically a temperature higher than 20 Celsius, then we can use this relationship to calculate what is the reaction rate. So also notice that it's divided into two regions, right? So when theta is between 20 Celsius and 4 Celsius, we're going to use a theta value of 1.135. Okay, so it shouldn't be theta here, it should be temperature. Okay, well, if the temperature is above is above 20 Celsius, well, it's below 30 Celsius, it's going to take a value of 1.056, right? So this is how the temperature might affect the reaction rate or the deoxygenation rate. Okay. All right. So actually, I received some of the comments regarding how we can solve the problems of 9-1 and 9-15. This is about the calculation for the MBOD, and also the theoretical BOD, right? So if we look at the problem 9-1, or the first problem here, it is telling us that we're trying to deal with the glutamic acid. So from these reactions here, so let's try to look at how the glutamic acid are being is consuming the oxygen. So from this first reaction, we can see that each mole or each number of the glutamic acid are going to consume 4.5 number of the oxygen, right? And it generates carbon dioxide and water, and also ammonia, right? So further, the ammonia can get oxidized and to form these ions here, and there's no way that these ions can get further oxidized. So what this means is that each number, let's say each number of the glutamic acid, C5H9O4N, is going to react 6.5 numbers of the oxygen here, right? So based on that, so basically this is how we can determine the theoretical oxygen demand. This is just based on the stoichiometry. So further, we can look at what is the molecular weight of this glutamic acid, and it turns out to be 147 grams per mole. Okay, so based on the mass concentration of the glutamic acid, we can calculate what is the molarity of it, right? So that's going to be 150 milligram per liter divided by 147 gram per mole, and then we should multiply that by the molecular weight of oxygen and also this number for the stoichiometry, which is 6.5 multiplied by 32 gram per mole, right? 32 is the molecular weight of oxygen. So this is how we can determine this theoretical oxygen demand. And this value actually turns out to be 212 milligram per liter. Okay, so this is how we can work out this reaction here if we trace the first and second equation. So we also have the problem 915, which is trying to let us calculate what is the MBOD. So as you can see, the MBOD means to convert the nitrogen into the species that cannot get oxidized anymore. And then basically the nitrogen is coming from the this reaction here. So we know that once ammonia gets dissolved into water, it's going to form these ammonium ions, right? Ammonium ions can further get reacted with the oxygen and then form these species here. So basically, based on this relationship, we know that the MBOD, for each gram of the nitrogen, we're going to require 4.57 grams of the oxygen. So what this problem is really asking us to calculate the MBOD is to find out how many grams of nitrogen are there in this solution. So it's saying that it's assuming the concentration of the glutamic acid is 0.1 millimole or millimolar per liter, right? So if we know the molarity of the glutamic acid is 0.1 here, then we also know that the molarity of the nitrogen is actually also 0.1 milliamp here, right? So what we need to do is to first calculate what is the total mass or the mass concentration of the nitrogen. We need to multiply that by 14, right? So this is basically 14 grams per mole. And then we should multiply this MBOD constant here, which is 4.57 grams of oxygen per grams of nitrogen, right? And this can this actually turns out to be 6.4. milligram oxygen per liter. Okay. So remember this NBOD here, or 4.57 here, corresponds to how many, or what is the mass of the oxygen that's required per grams of the nitrogen. So if we can find out what is the total mass of the nitrogen in the solution, then we can calculate what is the NBOD, right? Okay, so basically that is the BOD and NBOD. And then when we further look into the river water quality, we introduce the DO sag curve, right? So the DO sag curve basically tell us what is the composition of the dissolved oxygen as a function of time. So the dissolved oxygen concentration is going to decrease first, which is because of the deoxygenation, right, coming from the oxidation of all the organic chemicals in the water, right? And then this concentration is going to come back again, which is because of the aeration in the water, where the oxygen will get dissolved in the water, and also there are photosynthesis for the plants or planktons in the water. So the oxygen concentration will come up. And also it is because the organics are being consumed, right? So the dissolved oxygen, also the deoxygenation rate is smaller compared to the aeration rate. So this is going to create this type of curve, and then we call this as the DO sag curve, okay? So one point that you might get quite puzzled is that when we're trying to solve for this DO sag curve, so instead of calculating the dissolved oxygen concentration, we were using the oxygen deficit, okay? Oxygen deficit. We're using the oxygen deficit as the parameter to solve for the dissolved oxygen, okay? So for example, this is the equation that we constructed. We're considering that there is the deoxygenation, right? Multiplying the remaining organics in the water, and then there's aeration, which is replenishing oxygen in the water. So instead of building a relationship to calculate the dissolved oxygen, we were using the oxygen deficit, which is shown as the parameter D here, okay? So just based on its name, the deficit means how much it's away from the saturation, right? So let's say at the end, or so many days away from this mixing point in the beginning, then the oxygen concentration, or the dissolved oxygen concentration, is going to get very close to the saturation dissolved oxygen, right, or DOS. Then at this point, the deficit is 0, right, which means that it's already at its maximum concentration there. Well, at this critical point where the dissolved oxygen concentration is lowest, at this point, the deficit is at its maximum, right? Which means that it's most away from the saturated condition, okay? So theoretically, if we want to plot out what is the deficit, or the oxygen deficit as a function of time, then it should look something like this, right? The oxygen deficit at the beginning is not 0, which is mainly because the mixing of the river water and the wastewater. Sometimes it can get very close to 0 here, which basically means that the wastewater doesn't contain, the wastewater has a dissolved oxygen concentration that's at the saturated point, right? And then as the time goes on, then the oxygen deficit will go further higher and higher. And this is because the deoxygenation, which is basically the oxidation of the chemicals in the water. And then further, the oxygen deficit will go down. And this is because of the reaeration, where oxygen further get dissolved in the water, right? And this is going to create us this DO sag curve. But if we really plot out the deficit, or the oxygen deficit in the water as a function of time, it should look like this, okay? So basically, if we want to calculate what is the dissolved oxygen at any specific location that's downstream of a river. So for example, we're dumping in the wastewater here, right? The river water is going this way. We know that the dissolved oxygen concentration will decrease and then come back, right? So let's say if we want to calculate any point, let's say we're interested in the concentration of the dissolved oxygen here. Then dissolved oxygen, then we just need 4 parameters, okay? So we'll need 4 parameters. So first is this dA here. So the dA is the oxygen deficit at this mixing point, okay? So the oxygen deficit at this mixing point, according to definition, basically the oxygen deficit, D is equal to DO saturated dissolved oxygen minus the current dissolved oxygen concentration, right? So the dA is just the saturated dissolved oxygen concentration minus the dissolved oxygen at this mixing point. So how do we calculate this dissolved oxygen at the mixing point? We can use the mass balance, right? So the mass balance tells us that the concentration, or the dissolved DO here, should be calculated by the flow rate of river water or wastewater multiplied by the DO of the wastewater plus the flow rate of the river water multiply the DO of the river water and divide it by the total flow rate here. Okay. We also need the second parameter, which is the remaining organics at this mixing point. So the remaining organics at this mixing point, again, we're going to use a mass balance. That's the remaining organics in the river water and then the remaining organics in the wastewater. We're using this basically weighted organics concentration, right? So this is the first 2 parameters, and typically we're going to use these equations to calculate what is the mixing result of the dissolved oxygen or the oxygen deficit and also the remaining organics. We also need 2 more parameters, which is the deoxygenation rate, right? And also the irradiation rate. Okay, once we have all of these 4 parameters, we can directly plug in this equation here to calculate what is the oxygen deficit at any time. Okay, it doesn't matter if it's 1 day, 2 days, or 1 year away from the mixing point. As long as we know these 4 parameters, we can calculate what is the oxygen deficit. And as I mentioned, once we know the oxygen deficit, then we can calculate what is the dissolved oxygen concentration, which is basically the reverse of this equation, right? If we rearrange this equation, the dissolved oxygen at this point is equal to the saturated dissolved oxygen concentration minus the oxygen deficit, okay? So in order to calculate what is a BOD at any specific time or at any distance after or downstream of this mixing point, then we just need to find out these 4 parameters and then plug them in, right? So this is about the concentration at any specific distance. So if we're interested in this critical point, right, this lowest point, we can also use this equation. So as I've introduced in the class, the origin of this equation is just taking the derivative and then set them to be 0, right? And then we can basically find out where is this critical time and also what is this critical oxygen deficit. Okay, so once we know the deficit, we can know what is the dissolved oxygen concentration. Okay, so actually one thing that I missed in the class is about how we can calculate the deoxygenation rate constant and also the irradiation rate constant. So we introduced that here. We need to find out these parameters, right? Parameter 3 and parameter 4. And actually, if you go through the textbook, and I'm pretty sure that you already went through this calculation based on the equation, right? So the deoxygenation rate, or the KD, can be calculated by K plus U divided by H multiplied by eta. Okay, so the K here is the reaction rate that we determined from the BOD test, okay, which is the BOD rate constant. And also the U here is the average velocity of the stream flow, while the H is basically the average depth of the stream or the river. And the eta here is the bed activity coefficient. Okay, so this is related with how active the river water is, right? So if we find out these parameters from the table here, so basically we can plug in the k equal to 0.2, and then u, we should use the parameter of the river water, which is 0.5, h is 3, and then multiply by 0.4. So we can basically use this equation to calculate what is the deoxygenation rate. It turns out to be 0.27 per day. Okay, and similarly, we can use the equation from the textbook to calculate what is the reaeration rate. Okay, so the reaeration rate should be equal to this constant 3.9 multiplied by the velocity to the power of 0.5, and then divide by the h to the power of 1.5. Okay, and then basically this turned out to be actually 0.53 per day. Okay, so this is actually something quite interesting. So we just introduced how to calculate these parameters here. But if we just think of this equation more logically, so let's say we have river water here, and then we have mixing point. Let's say the pipe is dumping in wastewater. So for this reaeration, which means that oxygen is getting into the water here, if the velocity of the river is more rapid, okay, it's more quick, so will there be more oxygen getting dissolved or less oxygen getting dissolved? There will be more, right? This is mainly because the faster the river flows, then the more turbulent it becomes. So if we have more turbulent condition, then we might easily form these ripples, right? These waves over the water, and then this will create us much more surface area for the oxygen to get dissolved in the water. Okay, well, if the flow rate is too slow, then it's just going to flow still, right, very peacefully, and then this is the only surface area for us to dissolve the oxygen. So that is the reason why if we have a higher flow rate or the higher velocity, then the reaeration rate is going to be larger. And this also applies for the height, okay, or the depth of the water. If we have really deep water here, then it's less easy for the water to get dissolved further deep into the, for the oxygen to get further deep into the water here. Okay, so you can also think of this process more logically if we are looking at the deoxygenation rate. Okay, and so here, so basically for your last homework, you also went through some practice when basically you can use the equation to calculate what is the BOD at any specific location downstream of the mixing point, right? So this is the example that I gave in the class, and I think it might be helpful if we just go through this example again. Okay, so let's say we have a city of certain amount of people, and it's disposing this wastewater into the river water. Okay, so we can draw out a schematic here. So we know that this flow rate is 1.05 meter cube per second. Okay, and also it has a BOD, or the ultimate BOD of 28 milligram per liter, right? We also know that the dissolved oxygen of this wastewater is 1.8 milligram per liter. Okay, and then we also have the condition for the river water. So the river water has a flow rate of 7.08 meter cube per second, and the velocity, so you should notice that this velocity u here should be a constant no matter whether it mixes with the wastewater or not. Okay, so the u is 0.37 meter per second. So also it provides us the ultimate BOD, which is 3.6 milligram per liter, and then the dissolved oxygen is 7.6 milligram per liter. Okay, so it also provides us the saturated dissolved oxygen, or the DOS, is equal to 8.5 milligram per liter. It provides us with the deoxygenation rate, which is 0.61 per day, and the reaeration rate, 0.76 per day. Okay, so as you can see, basically we don't need to use these two equations to calculate what is the deoxygenation or reaeration rate. Okay, so it also wants us to calculate. So basically, with all of this information, it also further assume that there is complete mixing, right? The mixing here is very complete, and the velocity in the river is the same upstream and downstream of the outfall. So basically, this velocity here is always the same, flowing in the same direction, right? So first, it wants us to calculate what is the oxygen deficit and what is the ultimate BOD just downstream from the outfall, which is just after the mixing, right? So basically, what this problem asks us is to calculate what is the initial condition after the wastewater mixed with the river water. Okay, so it is asking us how to calculate these two parameters. What is the oxygen deficit at the mixing point? What is the remaining organics, which is the ultimate BOD at this mixing point, right? So what we can do is that the dA, basically, this is the first parameter, right, is calculated by the DOS minus QW DOW plus QR DOR divided by QW plus QR. Okay, so if we plug in all of these values, that's going to be 8.5 minus the river water flow, the wastewater flow rate, 1.05, multiplied by 1.8 plus 7.08 multiplied by 7.6, right? So if we trace these values here, and then divide that by the total flow rate, which is calculated by 1.05 plus 7.08. Okay, so this turns out to be 1.6 milligram per liter. Okay, so this is the oxygen deficit at this mixing point. So we got this first parameter down. And then for the second parameter, which is the BOD, or the remaining organics at this mixing point, it is calculated by directly using this mass conservation law, which is QW LW plus QR LR divided by QW plus QR. Okay, so if we plug in these values, it's going to be 1.05 multiplied by 28 plus 7.08 multiplied by 3.7, and then divide by 1.05 plus 7.08. So that's going to be 6.75 milligram per liter. Okay, so this is how we can solve for the first problem. And then for the second problem, it is asking us what is the dissolved oxygen 6 kilometers downstream. Okay, so as we have introduced in the class, this is a more logic way of asking the question, right? So instead of asking what is the dissolved oxygen 1 day downstream the mixing point, 1 day downstream of this polluted water being dumped, we're normally very careful, or we care about the dissolved oxygen at certain location, right? So, but what we need to do is to convert this location or this distance information into the time information and use the solution for the DO stack curve, right? So the way or the method we use is basically we can calculate the time by dividing this distance, 16 kilometer, by the velocity of the river water, right? And that is equal to 0.37 meter per second, and here is 16,000 meters. So it turns out that the time that's needed for the water to flow over there, that's going to be 0.5 days. And of course, we have to convert these seconds information or the time information into days by using the, let's say, each day is 24 hours and each hour is 3,600 seconds. Okay. So now you can see that we have all of these parameters. We have the dA, LA. We also have the deoxygenation rate and reaeration rate. We also have the time. So what we can do is we can directly plug in this equation here to calculate what is the oxygen deficit at this time, right? At this 0.5 days. So we can use that equation. So instead of writing out that equation, I'll just write out the answer here. So it turns out that the oxygen deficit at 0.5 days is 2.56 milligram per liter. Okay, so once we know what is the oxygen deficit, then the dissolved oxygen is just the saturated dissolved oxygen minus the oxygen deficit, right? This is how we define the oxygen deficit here. So that's going to be 8.5 minus 2.56, which is 5.9. Okay, milligram per liter. Okay, so this is the final answer. And from your homework problem, actually, they're using the same concepts here. So what we need to do is we should first find out what are these 4 parameters here. And then we should plug in these parameters into the equation for calculating the oxygen deficit, and then we can further determine the dissolved oxygen concentration. And I think for one of the problems, it's probably 9-29 here. So I think there's maybe a typo in the homework problem. So instead of using 28 Celsius, it should have printed 16 Celsius. Actually, that's the case for the earlier version of the textbook. But if we use the 28 Celsius instead, then you can find out that the deoxygenation rate is much higher, which is going to make the dissolved oxygen to be below 0. And we know that this is not going to happen, right? So in this case, after a certain time, the dissolved oxygen will just stay at 0, and there's no way that the dissolved oxygen can come back again. Okay, but basically that problem is using the same concept, except that we need to calculate what are the deoxygenation rates and the reaeration rate. Okay. So I also received some comments about the last problem for your last homework. So this homework is about this homework problem is about the river water quality. Instead of the river water quality, we're trying to look at the lake water quality. Okay, so we're using the concept of the mass balance here. So we're looking at a small lake, right? And let's say we just draw a lake that looks like this. So it is saying that the lake has certain dimension, 150 meters and 120 meters in terms of the length and width, right? It also has certain depths, right? The depth is 30 meters. So the lake is fed by a small pollution-free stream that has an average flow rate of 1.5 meter cube per second. Okay, so let's say this is the inflow here. So the Q is 1.5 meter cube per second. Okay. And then it says that there's a herbicide or certain chemicals that are detected at a concentration of 45.2 microgram per liter. Okay, let's say this C here, it turns out to be 45.2 microgram per liter. Okay, and also I mentioned that for this chemical, it actually can biologically degrade within the water, and it has a degrading constant of 0.22 per day. So with this unit here, you can actually see that if a rate constant has a unit of per day, it simply means that the rate is a first order reaction. Okay,
So if we want to know the reaction rate, then that is just K multiplied by C. Okay, so this is the reaction rate of this chemical in the water. So also it's assuming that the lake is at steady state condition and then it's completely mixed at the time of the sampling. So you can think of this as a CSTR, right? So the water is completely mixed within this lake here. So as you can see, we detected certain concentration of this chemical here, and we know that it's naturally degrading. But the result is that we're seeing this constant concentration of this chemical here, right? So theoretically, if there's no input of this chemical, then the concentration should decrease exponentially. But we're seeing that this concentration is constantly being detected. And what this basically means is that there is a mass input of this chemical in the water, right? Of this herbicide in water. And as I have already shown, the problem is surrounded by this agricultural land. So what happens is that the agricultural land is actually dumping in these herbicide into the water. So the problem wants us to solve what is the mass input of the herbicide in the water, okay? And to solve this problem, we need to find out what is the mass balance. We know that there's an input or the inflow of the water, and if we consider what is the mass balance of water, if a lake has certain volume, you can think of it as a bathtub at your home, right? So the bathtub always has certain volume here. So if the lake has an input of 1.5 meter cube per second, then it must have an outlet that's transporting this extra water out, right? That's gonna have the same flow rate, 1.5 cubic meter per second. Okay, and now if we try to build up what is mass balance in this lake here, then what we can do is we can set up dc dt. We're trying to look at what is the rate of change in terms of the concentration of this herbicide, and then we multiply that by the volume of this lake. Then that's going to be affected by this mass input, right? So that if we input more, the more we input into the lake, then the higher the concentration of the herbicide. So this term is going to be a positive term, right? So we also know that there is a natural degrading or the biological degrading of this herbicide, right? We know that this is a first order reaction. So this chemical is being consumed by this first order reaction. We should also include that term in this reaction, which is V multiplied by K multiplied by C. Okay, so this is the degradation term. And what we also need to notice is that not only the chemical is being degraded in the water, it's also being transported outside the lake, right? So we need to consider this process, which is Q multiplied by the concentration of the chemical in the water, okay? So you may notice, well, there are quite a lot of terms. Then do they describe the same thing, right? So we can do a quick check, basically, is to look into what are the units on both sides of this equation here, right? So on the left-hand side, you can see that the volume of the lake has a unit of meter cube, right? The concentration, we can basically set that up. You can see the concentration is microgram per liter. We can just use gram per liter or the gram per meter cube, okay? And then there's 1 over time, right? So this turns out to be gram per second, okay? So if we ignore this mass input term for now, because this is what we are trying to solve for, and then if we look at this term here, it has a unit of meter cube, right? K has a unit of per day, so that is basically equal to 1 over S, right? So the concentration has a unit of gram per meter cube, right? So basically, this is the same unit we're trying to solve for, right? And if we look at the third term here, then that's going to have a unit of meter cube per second for the flow rate, and then for the concentration, that's gram per meter cube, Okay, so the meter cube will get canceled. We still get this gram per second, right? So each of this term represents the same thing, that is the mass flux of the herbicide in the water. So we further know that this lake is at steady state, which just means that the concentration doesn't change as a function of time, which means that this term is equal to 0. So now the mass input is just going to be equal to V multiplied by K multiplied by C plus Q multiplied by C. Okay? So now we can start to plug in all of these numbers here, right? So the volume is equal to 150 multiplied by 120 multiplied by 30. You have the unit meter cube, right? Multiplied by 0.22 per day, right? And then we should multiply 42.2, 1 over day, 45.2 microgram per liter. We need to further convert these units into standard units, right? And then plus the flow rate, 1.5 meter cube per second, multiplied by the concentration, 45.2 microgram per liter. Okay, so I won't convert all of these parameters or all of these so all of these units here, but what it turns out is that the answer is the same as the value that's given in this problem, which is equal to 11.2 kilogram per day. Okay, so it is about this problem here. So basically it's using the concepts of the mass balance over this entire lake here. So this is that's all about the water quality and also the river water quality. So so the second section we learned about is water treatment, right? Specifically, this is about the drinking water treatment, not the wastewater treatment. So that's why it needs a very strict standard in terms of the processes for removing those contaminants and also the hardness, the bacteria from the water, right? So again, if we want to point out what are the major processes that we want to learn about, so we first learned about the coagulation, flocculation, and clarification, right? So this is a process that's using the surface charge of the particles. So that's why we want to put in the polyvalent ions to coagulate all of those colloids in the water. And then we also learned about the filtration, right? And more specifically for the groundwater treatment, we need to calculate what is the hardness or how we can soften the water, right? So in terms of the coagulation, again, this is trying to quickly review the contents we learned, right? So we want to put in the polyvalent or trivalent ions. We can put in the aluminum sulfate, right? So aluminum is a trivalent ion. So based on this equation here, you can see that once we put in the aluminum ion into the water, it basically generates these hydrogen ions. So if I ask, what is going to happen if we put in these coagulants in the water in terms of the pH? So the pH is going to reduce, right? Simply because we generate these hydrogen ions from the water. Okay, so the same thing will happen if we introduce the ferric ions into the water. Okay, and further we introduce the rapid mixing when we're trying to dispense the coagulants in the water, and also introduce the flocculation where we are going to use a smaller mixing speed to suspend the particles and then further promote the coagulation and flocculation. So here we introduce that if we want to calculate what is the volume of water, what we need to do is just multiply the flow rate by the residence time, right? So you can see from the homework problems this time that if we know the flow rate and we know the retention time or detention time or residence time, whatever they call them, so if we just multiply the time by the flow rate, then we can design what is the volume of this reactor or the flocculator, right? And in terms of the hardness, so in the class, I demonstrated how we can calculate the hardness of water if we already know the concentrations of all of those ions in the water, right? So we're specifically interested in the polyvalent ions, right? For example, calcium, magnesium, and also the trivalent ions, the ferric ions. Okay, so but we showed that for most of the water system we're dealing with, the hardness is just calculated, just determined by calcium and magnesium. Okay, so we further introduced that the hardness or total hardness can be separated into carbonate hardness and non-carbonate hardness. So the carbonate hardness and non-carbonate hardness are basically determined, or is or their relationship can be shown by the alkalinity and total hardness there. So I give a very simple example in the class by just using those bar graphs, right? So here I won't go through the further detailed calculation for this problem here. So this is an example problem on your textbook. So you can probably go through this problem again. So basically it wants us to calculate what is the total hardness, the carbon hardness, and also the alkalinity that's in the water, right? So if you already know what is the mass concentration of the calcium and magnesium, then we can convert them into the equivalent mass concentration of the calcium carbonate, right? So what we first do is we can divide this mass concentration by the equivalent weight of the calcium. So equivalent weight of the calcium is 20 grams per equivalent, right? Magnesium is 12 grams per equivalent. We can divide these mass concentrations by the equivalent mass concentrations, and then multiply that by the equivalent weight of the calcium carbonate, right? So based on that, we can plot out the bar graphs, right? Let's say this is the calcium, this is the magnesium, and we further know that the alkalinity is just the bicarbonate ion in the water, because in this water there's no carbonate ions, or there's no hydroxide ion, because the pH is 7.2, right? It's under neutral condition. Let's say the alkalinity looks like this, okay? Okay, and this is cations, anions, right? This is calcium, magnesium here, okay? So under this situation, the carbonate hardness is just the alkalinity here, okay? So basically this carbonate hardness is total hardness or alkalinity, whichever is smaller. So you see that the alkalinity is smaller, so the carbonate hardness is in this region here, right? And it's the same as the alkalinity. So if we're interested in the non-carbonate hardness, then that's just gonna be this region. Okay, so I know that the definition of the hardness, carbonate hardness, and non-carbonate hardness is quite complex here. So it would be good that you go through the textbook and then try to go through these concepts here, or you can work through the example problems or the homework problems to better understand this process. So we also mentioned about the sedimentation, right? So you have a homework problem that's trying to let you calculate what is the volume of the sedimentation basin. So the concept or the major parameter we're interested in is the overflow rate. So overflow rate is just calculated by the total flow rate divided by the area of the sedimentation basin, right? The surface area. So let's say if we already know what is total flow rate of the water treatment plant, and we know the overflow rate, we can just rearrange this equation, right, to calculate what is the surface area. So this similar concept actually applies for the filtration problem. So you can see that we're using basically the similar equation to design the filtration process and also the sedimentation process. So one thing we need to pay attention is basically this loading rate here. So as we have introduced in the last class during the video, so this loading rate has to be below certain critical values, right? So for the sand filtration system or the rapid sand filters, this value has to be smaller than 235, right? And in terms of the dual medium or the multiple medium filtration, this value can be smaller than 300. Okay, so basically these units are meter cube per day per meter square. Okay. Okay. So you also worked through these two problems from your homework there. So for this first problem, which I think is 10-24, okay, so it wants us to design a rapid sand filter systems. Okay, so for each of the sandbox, it has a surface area of 10 meter multiplied by 10 meter, and then we know that the total flow rate is 0.8 meter cube per second, and we also know the loading rate here. So if we use the equation for calculating the loading rate, that is calculated by Q divided by A, where A is going to be equal to Q divided by V, where the V is the loading rate, right? So basically, first we need to convert all of these units into standard units, right? So the flow rate is already in standard unit, which is 0.8 meter cube per second, okay? And for the lower one here, we basically need to convert day into seconds, right? So each day is 24 hours multiplied by 3,600 seconds, okay? So that's going to be 110 divided by 24 multiplied by 3,600 seconds. And here we have the meter cube. And here we have second, and then meter square. Okay, so this turns out to be 628 meters square. Okay, so basically this is the total surface area that's required by this rapid sand filter box. Okay, we know that each of the box has a dimension of 10 meter by 10 meter. Then the total number is just divide this A by the area of each sandbox. Let's use AS here. So that's going to be 628 divided by 10 multiplied by 10, which is 6.28. Okay, so here's the problem. We introduced in the class that we have to use even number of the filter systems, right? So we can either choose to round up, which is going to give us 7, and we need to use even numbers, which means that it's going to be 8, or we can round down to 6. So which one should we use? So let's say if we have a lot of money, of course, the more we build, the safer we are. But that's also restricted by the budget and also the space we're talking about, right? So here, we should explore the option of using 6 rapid sand filter boxes. So what we want to make sure is that if we use 6 number of them, the loading rate should be below 235 meter cube per day per meter square. Okay, so the way we can calculate that is if we know that there are 6 of these sand filter boxes, then we know that the total area is going to be 6 multiplied by 10 multiplied by 10, which is 600 meters square. Okay, so then we can calculate this loading rate, which is Q divided by A, right? And you can actually find out that this value is indeed smaller than 235. Okay, so what this means is we're okay to use this design here. So basically we're going to require 6 of these rapid sand filter boxes. So for this second problem here, which I think is 10-26, it's trying to let us design a new type of filter, which is dual media filter. So we introduced in the class that the maximum loading rate is actually 300 meter cube per day per square meter, right? So it wants us to build this filter instead of this standard filter in 10-24, while the flow rate and the dimension is still the same. So how do we approach this problem? We can still use the same method to calculate what is the total surface area that's required, which is Q divided by V, right? So again, here you should notice that the loading rate is now has a new value, right? Instead of using 110, we should use 300. So it turns out that this value is 236 square meter, okay? And then we can calculate how many filters we need, A divided by the surface area of each filter, right? 236 divided by 100, which is 2.36. So we can either round it up to 3, and then since we need even number of the filters, we should choose 4, or we can round it down to just 2 here, okay? So which one should we use now? So let's say that we try to be economic again, right? So we'll use 2 numbers of filters. We need to make sure that the loading rate is smaller than the maximum loading rate. So how do we calculate this new loading rate here? So this V then should be calculated by Q divided by A, which is 0.8 meter cube per second, divided by 2 multiplied by 10 multiplied by 10 meters square. Okay, so if we further convert this second into hours, you can find out that actually this new loading rate is 345.6 meter cube per day per meter square. Okay, so this new loading rate is larger than the maximum loading rate. Okay, which means that we cannot be economic here. We cannot choose fewer number of filters. We have to use a larger number of filters so that we can safely design this filter. It doesn't overload with the water. Okay, so this is how we can choose the options to design the filtration systems. And I hope that by introducing these problems, it help you understand some of these equations or some of these designing processes. So that's all for this help session.